Okay, yeah. Hi, thank you so much for joining today. This is going to be our last workshop in the crash course workshop series. So in this workshop and in some of the past workshops, we've been looking at some interesting machine learning topics, but from more of an applied perspective. So yeah, I find that it's really interesting to look at learn a concept through solving a problem. So that's kind of the style of our workshop. And today we'll be looking at something I think it's very interesting. So we're going to be looking at recurrent neural networks today. And this is a kind of where you learning sequences because of how it's designed. And the problem we'll be looking at today is generating Shakespearean text. So at the end, we'll train the model so that it'll write like Shakespeare, which should be pretty interesting. Yeah, so let's move on to the next slide. Yeah, this is just to set up the problem. So the problem that we're looking at today is we want to make the RNN model generate Shakespearean writing. So as a classic example, something like this. So to be or not to be, that is a question. So kind of that style of writing, that's the kind of language that we want to generate using the model. So that's the problem. And the steps that we're gonna take to solve that is, so it's shown here. It's kind of similar to some of the other problems that we saw in the other workshops. But first, you always start off with a data set. So in our problem, we'll be using Shakespeare's existing writing. So that will be what the model would be learning from. And then if we just take Shakespeare's text, the model's not going to be able to directly take that and learn it. So that's why another important step is data processing. So how do we take that writing and convert it into data that the machine and the model can understand? And then once the data is ready, it'll come down to the model. So this is the central part of it. So the model, building the model and training the model. So here we'll take a look at some of the concepts involved in the RNN architecture. So this step will probably be where a lot of the conceptual knowledge might come in. And finally, you have the model trained, it's just learned the data set. So now we can use it to solve the problem. So it'll be able to generate text, and based on what it's learned, it'll be able to generate writing that's close to the kind of writing style that Shakespeare uses. Yeah, so that's the overview of the steps that we'll be taking today. Okay, first, the data set. So there is a data set of Shakespeare's writing that can be found on TensorFlow. So this is the data set that we'll be using. And TensorFlow has this existing function that's used to download files from an URL. So this is the URL. And this will be how the data set will be obtained. So you can see on the right side here, this is an example of what the data set has. So it's just the play, right? So this one, it's the typical Romeo and Juliet play. Yeah. So this is what the data set looks like, just if you look at it directly. And from a different perspective, you can also get some, I guess you can call it statistical information. So I've listed a few here. So you can see the length of the writing is this many characters. And this part is more important. So you want to get how many unique characters there are in this text. And what's important about this is this will make up the vocabulary. And of course, vocabulary is important because this is what you'll be using to form your writing. So this is an important parameter that we'll use in the later steps as well. Yeah, so this is what the data set looks like. Okay, and then, so we have this writing, but we want to represent this text as data. So this is the kind of steps that we have to go through to make it more machine understandable. So when you're preparing the data set for training, you have to convert the string that you have. As you can see here, you have to convert it into numeric IDs. And how we do that is we first, yeah, I made a quick diagram below here. So let's say you have this, your string is like this. So you first split this text into tokens. So just split it into characters, and you have existing string functions that you can use to do that. And then after you split it, you can convert it into character IDs. And for that, there's is also a predefined function that you can use. So, and you can see here, here's where the vocabulary come from. You'll have to use that vocabulary that you've gotten from before, and you use it here so that you can generate the character IDs accordingly. So then now you can see it's no longer just human readable text, it's character IDs, which is easier for the model to understand. So then now you have this, then you can feed it into the model for it to learn and train and understand it. I've also put the other direction here. So remember today, our problem, we want to generate text. We want to generate Shakespearean style writing. So after we train the model, we have to make it generate text. So then at that point, we will be going in the other direction, right? So then you'll be going from numeric IDs because that will be predicted or generated. And then you want to interpret that ID into human understandable writing. So then, yeah, as you can see here, now you have to go from numeric ID to string. And similarly, this is just going the opposite direction. So now you have the character IDs, you convert it into tokens. Yeah, here you also use the vocabulary and this function. And then you join the tokens into a string. So that's sort of the data processing that's involved. Okay, I see a question. What are the character IDs? So this is like okay, let me go back. So remember when we talked about unique characters, so this is like how many unique characters or vocabulary there are in that writing. So then in this data set, there's 65. So then as a possible way of assigning the IDs to the characters, you can do maybe A is 1, B is 2, etc., etc. And then at the end, you have a number that corresponds to each of the characters. Because if you just have X, Y, and Z, it's a bit, because it's string, right? It's kind of hard to do math on it. So then if you convert it into IDs instead that corresponds to that character, then it makes it easier for the model to understand it. Yeah. Oh, token. Okay. The difference between token and character ID. Yeah, I guess the wording is a bit strange. Tokens are essentially just the characters that was extracted from this text. So this would be the text, and then this part would be tokens, and then you convert tokens, which are basically characters, into these character IDs, which are numbers. Yeah. Okay, yeah, no problem. yeah, feel free to let me know if you have any questions along the way. Yeah, so that was the first part of data processing, representing text. Now there's another part of this. So you have, sorry, let me go back. You've converted this writing into numeric data, but when you're training it, you want to put it in sets so that it's easier for it to train. And what this means is we should probably go through the steps here. So first, what it involves is basically these steps. So first you convert. So let me take a step back maybe. So first you have this, okay, yeah. This also considers a part of this processing. So recalling this last slide, you have the text and the characters, and they're represented as an array. And remember we said we want to convert it into IDs. So now they're represented as numbers. After you have this, this is just an array, right? But we want a data set, which would be more friendly for the model. And you would be using this, again, this function here. And this function would convert this text array into scalar character elements. And what this means is basically in this image here, you used to have this array. And after you pass it through that function, you would get a data set of it instead. So this is not a very, it's a bit hard to visualize it, but you can see it's no longer in an array, and these character elements are just by itself. That's why it's described as scalar. And because of this, you can also use this other function. So remember in the beginning, we said RNN, this recurrent neural network model that we're looking at today, it's really good at processing sequences, and writing is a form of sequence. So we want to group these characters into sequences of a certain length, and then we use that to train and learn from that. So then this is what it's doing here. And how we, first you use that function, and then you would be shifting through the characters to produce sequences. So you can see here, let's say, as an example, you want the length to be 2, as shown here. Then you start from the beginning, and you group 2 characters together, and that will be your input. So this will be used to train, and then you shift it forward 1 step, same length, and that would be the target. And the target is basically a fancier. Also, sometimes a target is called a label as well. Yeah, there's a bunch of names for it, but essentially this is like the answer key, because when you're if you think about it, not only for models, but for anyone, humans, even humans, for us to learn, to solve some kind of problem, we have to have the input and also an answer key so that we know where we made mistakes so that we can improve. So this is kind of the formatting that the data set would follow, so that this can be, so that the data set is in a better shape for training. The last step is just to, so you want to batch the sequences together. So feed it through one by one, and then shuffle the data set to create some randomization. So that's the end of data processing. Now we have the training set. Yeah, so we've been looking at the problem more directly in the data steps. Now, since we're getting into RNN model territory, just want to take a few minutes to explore the background knowledge about the different concepts involved in RNNs. Yeah, so let's take a look. Yeah, so first, I was going through different articles to see what would be useful, and I found this article, and it mentions this really nice example that gives a good intuition behind how the RNN learning works, and basically it involves sequential memory. So you can do it. You can do it here as well. You have the alphabet, and then you can try saying the alphabet forwards or backwards order, and try to see which one is easier. A different, slightly tweaked version of this is you can start saying the alphabet at a certain character and then go on. Did you struggle with the first few characters, but it got easier afterwards? So I'm sure it's probably easier to say the alphabet in forwards order, and it also gets easier afterwards than when you first start at a random character. And this is all because of the way your sequential memory is trained. We're so used to going from A, B, C, and then going down. And so that's kind of, so it gives you an idea of how sequential memory works. And yeah, so now that we have a better intuition about sequential memory, let's take a look at the RNN architecture itself. So RNN, it's, how should I say this? So before we talk about RNNs, I'd say RNN is a special kind of feed-forward model. And what a feed-forward model is basically you have an input. You feed it through the model, and the model basically just does some complicated computations that I'm not going to go into details today. But essentially, it will generate an output. And in that computation, a very important parameter is the weight, which the model would be training and tweaking to optimize the predictions. So that's how it improves itself. And that's how feed-forward models work. And what makes RNN unique is that, as you can see in this example here, it takes previous output and then use it as input. And these previous outputs are represented as something called hidden states. So then you would be passing into the input as well as the hidden state, which is a representation of all the previous things that you've learned. So then, and so because of the way this is designed, you can now, so you can see now why this is good for processing sequences, because first, sequences, sometimes you don't know how long a sequence could be, right? It could be arbitrary. So this is good for that. And now that you sort of have a loop, you're considering time as well into the computation. And the way that we talked about, which is an important parameter that you try to optimize, it's shared across time. So that's where the time aspect comes from. Should I show this example? Yeah, sure, we have some time. So this is the really nice article that I was going through, and it has a really nice example that will probably makes it easier to understand. So in this example, you have this sequence. And remember we said you pass in the input. So you first pass in the first word in the sequence and you get an output. So then now you have a hidden state, which is a representation of what you learned from that. And then you continue on. So this is the next time step. And then you feed in a new input in that sequence. But you also have the previous hidden state, and then you generate the output again. And you go on and on. So then you can see at the end, what you're learning considers all the previous words in the sequence. And then you can make your prediction from that. Yeah, so that's basically how the RNN architecture works. And the next few slides just go into a bit more detail about how the training works. So like I said in the previous slide, an RNN, if you just look at it statically, it looks like this, but really there's a time component to it. So you can unroll the RNN through time, which will make it easier to understand how, like, what actually happens in the RNN. So remember we said when we are learning the model, we have to, there is a target or a label, whatever you call it. And then you take that and then use that to gauge how wrong or how correct your prediction is. So then from that, you can get the error, which you back propagate. So you pass through from the last, pass it through from the last to the first time step. And then you would calculate the loss at each time step and then update the weight. So yeah, last slide, we talked about how the weight is optimized. This just goes into a bit more details about how the weight is improved so that it makes better predictions. Yeah, essentially, there is an error that you calculate from the prediction and the answer key of some sort. And using that error or loss, that's how you improve the weight so that it'll generate better predictions. Yeah, and this is also a common problem that you may encounter with RNNs. So it's called the vanishing gradient problem. And with this problem, you basically have just shorter memory. So you have short-term memory. In the last slide, we talked about back propagation. So when it's propagating the error, the gradient is something that you calculate to optimize the weight. And this calculation, as you can see, when you go down, your calculation is dependent on a previous layer. So then what happens as a result of this is that because it's dependent, it causes the gradient and weight adjustment to shrink. So then you can see because of this, you would have short-term memory. Maybe a good example, let's go back. A better illustrated example is here. So you can see here, yeah. So you can see at first it's able to remember a lot of what it learned from before. But as it goes on, the later words in the sequence would take priority. So you can see the color coding here. So then in the end, you sort of forget the older memory. And that could be a potential problem. So then, yeah, I'll just finish this slide here first. So then how you solve that problem is there are two special kinds of RNNs, LSTM and GRU. I don't think I'm going to go into too much details today since this is going to be a whole other topic on its own. But basically, just to give you a quick overview, these are, so you can see the diagrams here. They have additional gates that'll selectively update the long-term memory. So then that way you're considering more of the long-term memory and not just the short-term memory. Yeah, if you're interested in more, I will post the slides later. And there is a really nice article that has animated steps on how this works. Sorry, let me just take a look at the questions. How does it deal with long or conjoined questions? Sorry, could you elaborate on what you mean by conjoined or long questions? Or just how does it solve that short-term memory problem? Yeah, feel free to let me know in the chat. Oh, yeah, I see it. Oh, are you asking specifically about? Okay, yeah, let me actually read out the question. So the question is, how does it deal with long or conjoined questions? So basically questions that have and or longer sentences. Are you asking for just RNNs in general or for that particular example? If you are referring to RNNs in general, so if we just have an RNN like this, it would have this short term memory problem. So that's where these two types. So these are kind of like special types of RNNs. So this will be where it comes in. So then it will have gates that'll pass that selectively updates the longer term memory. So then the longer sentences will be considered. Does that answer your question? Yeah, okay, great. Yeah, so that was a quick overview of the concepts, and yeah, now we're back to the problem itself. So how do we represent that model in code, right? And yeah, TensorFlow has a lot of existing libraries that we can use to build the model. So we have this class here, and there are various functions that already exist that you can use. So I've listed a few important ones here. If we have time at the end, we can quickly look through the code as well. But you can see, so the GRU, which we talked about here, you can just use this function here, and then you'll have the RNN model. And in addition to that, there is also the input and the output layer, which these functions or these libraries represent. So the input layer, remember, we had processed our data so that it uses character IDs. But for further processing, sometimes we have to further embed it into more code. And embed it to a form that fits maybe the size or just the way the model is trained. So this is the input layer. It'll do some further embedding and coding. And on the output side, you have this dense layer, and this layer would be able to calculate the likelihood. So this is where it makes the prediction. It'll calculate the likelihood of each character in the vocabulary. And this is the important part. This is how it will be able to predict and generate the next character in the sequence. For training, these two would be important. So remember, we talked about, so when we're training, we take a look at prediction versus the label. And from that, we will be able to get the loss. And that loss is what we use to optimize and train better. And this is the loss function that will be used to do that. In addition to the loss function, you also have to have an optimizer. So the optimizer will be used to optimize the way to make better predictions. So these are all different components that will come into building this model and training the model. So then once you train the model and it's learned Shakespeare's existing writing, you can now generate the text. And how you do that is you just run the model in a loop. So this architecture is sort of similar to the diagram that was shown when we looked at how RNNs work. So you can see you can pass in the characters one by one. And at each time step, it produces a prediction, and the internal state is a representation of previous learning. So then you just run it through the loop, and then through that loop, it will be able to learn the sequence and consider the different characters as it moves through the sequence and time. And that's how it learns and makes the predictions. And essentially, once you make the predictions, you can use that to generate text. Yeah, so this is just a quick overview. Hopefully we'll have time at the end to demo the code, and then we can see in more details how this works. Yeah, so after you pass it through the model, then you can see an example of what gets generated. So first you have to give the model a prompt, because it will take that prompt. So in this example, it's the character Q. It will take that Q, and when you feed it into the model, it'll use what it's learned and make predictions for the next characters in the sequence. And what is generated is in here. So you can observe that the good part is you can see these are valid English words, and the sequence is even able to generate the text so that it's in the play writing structure. So you can see like the way they're grouping the sentences is sort of more boxed, and that's usually how plays are shown. And it even makes sense. The grammar even makes sense, but the only bad part about this is if you read through it, the content itself doesn't make sense. Yeah, so that's the hard part to learn, right? So you can see it's able to get some, it's able to understand and generate English words and some writing structure, yeah, which is quite impressive. Yeah, so yeah, and it even talks in a Shakespeare style as well. Yeah, so it's learned those characteristics as well. Yeah. Okay, demo time. Okay, we have time. Let me. So while I was thinking about what will be nice content to do for our last workshop, I found this tutorial from TensorFlow, which is where most of today's ideas come from. You can feel free to, I'll probably post the slides, so the link will be there. Feel free to try out this tutorial. It's really cool, and they have more details as well. Yeah, so just wanted to show the code side, since we mainly just looked at an overview of the steps. Let me quickly, yeah, so as always, you have to import the libraries, which we'll be using. And let me go back so that we can walk through the steps again, but instead in code. So you can see this is the function that I mentioned. So you can use that to download the data set from this URL. And then you read the data using the open function. This is like the common function that you use to open files. And you would have this, I think it would be an array of characters. And then you can even, so this is where the length comes from. You can use the length function to get how many characters there are. You can see for sanity check, you can even print the first few characters in the text. And the vocab, it's also gotten using these set and sorted functions. So sets, they're unique, right? And then it will sort it so that you would only get the unique characters, which would form the vocabulary. Yeah, which is an important part of understanding the writing itself. And then, yeah, this is the data processing part I was talking about. And you can see the function here. They're also just showing an example. So you have words like this, and you can use this function Unicode split. And you can see it used to be like this, but now they've separated out the characters. So you split it into tokens, which are essentially characters. And then this part, this is also the other function that we talked about. This will convert the characters as tokens. It will convert that into IDs. And you can see it uses the vocabulary because the ID, it's sort of related to how many unique characters there are, so vocabulary. And so that's something it has to consider. Yeah, so now you have this function that will be able to convert from IDs to characters. Yeah. So you would feed it. Sorry, I was thinking about it the other way. No, but it's yeah, the input will be characters, and then you can get some IDs. So you can see it's this will be how these writing will be represented as IDs. Now this part is the reverse that I was talking about. So now you go from numeric ID to string. Let's see. Yeah, so you take those IDs, and you, hold on. Did I skip something? Oh, here, right. Yeah, so you first have to use this function. And again, it uses that vocabulary. But now you're sort of inverting it. So then you would convert the IDs into characters, and now you would have characters instead. And this is the other inverse function that you can use to get the characters back into strings. So voila, these are the two directions of data processing that's involved. And then, so that's the first part of data processing. And the second part of data set processing, remember we want to generate it or convert it into a set. So here it has more of the code that does it. So here this is from before you will want the IDs first. So before it was just an example. Here we actually converted into IDs. So yeah, it's printed it as well. You can see it's just an array of characters, but these characters are represented as IDs. You use this function and it takes that and then convert it into a data set format. And this is just printing it. So you can see it's each character, it's individual now. And then you can set the sequence length. And then you would use that length and the batch function, and it'll be able to group the characters into your desired sequence. Yeah. So you can see, yeah, here it's showing it's still in its token form. If you want to see it in the string form, you can see, yeah, it's it has the same length, and it's cut these writing into these sequences. Yeah, there's a lot of calculations going on, but essentially what we just did was we cut the writing into a sequence. And then this is part about the input and the label. So essentially, this is also maybe it's better to look at this. Yeah, so the input would be this, and the target or the answer is basically this shifted. Because if you make a prediction, essentially it'll be the next character, right, in the sequence. And then by doing it this way, you would have the next character, the sequence. So you have the input, the target, and then you group up the sequences. This is some further dataset organizing. Yeah, so you can use that and then set some desired parameters that you like, the parameters or characteristics that you like the dataset to have, and then you would get the dataset. Yeah, so those are all for processing the data. Now for the model. Yeah, so I mentioned these here. Yeah, here. These functions, important functions, is also explained here as well. But basically, you can see you would what's the right way to describe it? Yeah, you would describe the architecture of the model in here using code, and you can see the input layer, the GRU layer, which is the RNN layer, and then you have the dense layer, which is the output layer that you make predictions in. So you define the layers that you like in your model here. So that's how you build the model using the code. Yeah, this is also a really nice diagram. So the GRU or the RNN is here. You have the sequences that has a certain length, and those are the input characters. And you have batches of it since they're in a data set. And then you feed it into the input layer. So it'll produce this embedding, which is just some further processing to make the character ID even easier for the model to understand. And you feed it through. And of course, this is on a time basis. So it's in sequences and time steps. And then you can see it passes along the states from before, and you use that states from before and the new inputs. You can use those to generate new output. And then the dense layer would be used to produce logits, which we mentioned before are just the likelihood of each character in a vocabulary. And that's how the prediction would be made. Yeah, so that's the model architecture by itself. And if you just want to train the model now, yeah, so we talked about the loss function and the optimizer, which is what would be used to learn and make better predictions. And yeah, you're basically just calling these existing loss functions that you can use already. Yeah, you've configured the model, and then you compile it, you specify an optimizer for that model, which is how it'll optimize the model. And then to train, you just call this fit function. Yeah, it's really nice once you can use these machine learning libraries, and then you just train it through a bunch of times. So the more, as long as you don't go overboard with the number of trainings, it should get better each time, because you're this might be an example, could be like you read this text for one time, you remember some parts of it, but if you go through again and again, you have a better learning. So this is why it's training for more epochs. Yeah. And then, yeah, this is the image that I showed before. So now that the model has learned the existing Shakespeare writing, it now should generate new ones. And how that's done in code is a bit more complicated, but I believe the important steps are just these ones here. So as always, you have to first convert, let me see, the strings into token IDs for the model to understand. And then you have the model here that you'll use. It's already trained, and it's able to predict what would be the most desirable character in the upcoming sequence. And you just take the last character, since that's your prediction, essentially. And then that prediction, you want it to do some math so that, yeah, there's a lot of functions that you can use as well, that will generate, because it's logits, so you sort of have to take that and then use that to generate the token. And this is more familiar for us. So this is also that conversion from token ID to characters. So then you would actually get back text and not just some random numbers that might represent that text. Yeah, so this is how it makes use of the model and make predictions. Yeah, so this is the main function that does the prediction. It just predicts one step. So to generate a sequence of predictions, you would just run it in a loop. And if you can just give it a prompt. So this time the prompt is Romeo in this example. And then you can see it's able to generate writing. Yeah, which is really cool. Are there, yeah, that's the, yeah, then now and then, yeah, the other ones, we're probably not going to go into more details today. But yeah, it's able to generate writing that's close to Shakespeare style. Really cool stuff. Quite magical, kind of. Yeah, that's all I have for today. Yeah, you're free to go, but feel free to let me know if you have any questions. Anything else you'd like to discuss?